So welcome Dr. Debendra Das Sharma. He is a Intel Fellow, Senior Fellow and Chief IO Architect in the Platform Engineering Group at Intel. If you work on PC Express, CXL, or UCIe, you likely benefit from his work. He helps stage the standard that powers modern computing. Debendra chairs both CXL and UCIe consortia and serves on the PCSIG board, drives some of the most transformative interconnect technology in the industry. With over 500 patents worldwide, some of his recognition includes Distinguished Alumni Awards from IIT Kharagpur, PCSIG Lifetime Contribution, and recently IEEE Computer Science and Society Mackenzie Technical Achievement Award. Please join me in welcome Dr. Debendra Das Sharma.
Thank you, Leticia. Greetings, everybody. I hope you guys can hear me fine. So I'll be talking about on-package memory with UCIe. It's a low power, high bandwidth, low latency, low cost approach. This work was done jointly with my colleagues, Swadesh and Peter from Intel and Rob from AMD. Here is the agenda for today. We'll talk about an introduction, the problem statement, then we'll provide an overview of UCIe, then I'll present a few architectural approaches to on-package memory using UCIe, then present its effectiveness, so some results, and finally conclude. On-package integration of chiplets, that is heterogeneous integration, especially between compute and memory, it is in mainstream compute across the entire compute continuum, right? We'll talk about a couple of bookends here, handheld laptop PC, as you can see in the example here. You got compute die, you got LPDDR on the package, and there the motivation is low power, board area constraints, cost, all of that. You got products from Apple, Intel, Qualcomm, etc. On the other bookend, you have AI HPCs servers, basically things like CPUs, GPUs, accelerators. Here, HBM is the interconnect, is the on-package memory. You got compute dies connecting to HBM. There is an example of Xeon and the NVIDIA's GPU. And the motivation here is to get high bandwidth, about 20 times bandwidth for the same capacity that you get using LPDDR. But it is 5 to 10 times more expensive. And the applications are very bandwidth constraints. And there are plenty of examples from AMD, AWS, Google, and we talked about NVIDIA and Intel. So the memory here is the bottleneck, less so on the LPDDR side, but more so on this space. So we need to think about on-package memory that is going to be power efficient and high bandwidth and cost effective going forward. Now we have been in a virtuous cycle of innovation for decades. Advances in computing capability, it drives newer applications, and those newer applications in turn demand a lot more compute capability. So recently, applications like AI, they need about 10x improvement in the in terms of the compute capability. As you can see in the graph here, it's a hockey stick, and this trend is not going to slow down. There has always been, and there will be, an insatiable demand for compute, heterogeneous compute, that is, memory bandwidth, memory capacity, storage bandwidth, storage capacity, interconnect bandwidth, all of those. And there is always something that limits the performance. Since the turn of the decade, we have been constrained by memory, right? On-package memory, and this memory wall is growing. And we need to do something about it. One approach is it is business as usual. You deploy more servers and more accelerators, deploy more of them. Your power budget basically goes up. We are already constrained by power. The data center, like Goldman Sachs has a projection that the data center power demand in the US was 3% in 2022, and the projection is it will be 8% in 2030 due to AI demand. Now, an alternative one, a better approach, in my opinion, would be to work and deliver a very dense compute on the package. We strike the right balance there between compute, memory, and I/O. This is where UCIe can help, both in planar interconnects as well as vertical interconnects on the package. And the challenge we are having with HBM is not on the HBM memory stack by itself, but it is in the interconnect between the SoC and the logic die. The SoC is shoreline constrained, so we just need to get higher bandwidth density. So our proposal that I'm going to go over today here is for on-package memory, it will use UCIe 5 and will show how that delivers scalable bandwidth in a power efficient manner and cost effective manner too. So we'll talk about more of that solution, and that logic die in turn can connect to a stack of HBM, or if you prefer, also to a stack of LPDDR dies. Now let's give a very quick overview of UCIe. There are some materials that I have listed here at the bottom. If you want a deeper dive, you can take a look at those. But UCIe 1.0 and 1.1, they addressed planar interconnects, 2D, 2.5D, and we'll see some pictures of that in the next slide. It's fully defined specification. It has a layered approach, and it can be implemented with interoperable IPs that you can get from different places, and you can connect them together on the package, and it will work. Now, the physical layer, it includes, the physical layer, it includes things like clocking, analog circuitry, channel, sideband, scrambling, descrambling, lane reversal, lane repair, basically the whole 9 yards there. The die-to-die adapter layer, it deals with reliable delivery of the bits across, and also effectively CRC and replay mechanism. And also it is capable of handling multiple protocol layers and dynamically arbitrating between them. And the scope of UCIe is from here to here. Now the protocol layer can be PCI Express, can be CXL, can be any streaming protocol, any proprietary protocol. Now with PCI and CXL, what happens is that you get the SoC construction issue gets addressed very easily. With IO, you get IO attached with CXL.IO and PCIe, and memory, of course, with CXL.mem, which is what we will talk about. Accelerator uses all three of them. And we also have support for streaming protocols. So this is akin to today people building symmetric multiprocessing cache coherent system using PCIe 5, and they're on their own cache coherent protocol. That's an example. It's a very well-defined specification. We have configuration registers, we have defined form factor, manageability, compliance, program, security, and all of those things. With 2.0, we addressed vertical interconnects. We're not going to go through that today. And 3.0, we doubled the data rate, which again, I'll briefly mention, but today's presentation is not about using 3.0 either. It's using the first UCIe 1.0, 1.1. But we doubled the data rate of planar interconnects from 32 gig maximum to 64 gig maximum. Now, this is a picture of standard package. These are planar interconnects. So standard package is 2D. It's cost effective, longer distance about 25 millimeter, bump pitch is 100 to 130 micron. Advanced package is for power efficient performance, a lot of wires through some kind of interposer or silicon bridge kind of construct. As you can see here, this is from Intel, this is from TSMC, this is from ASC. There are many more examples of this. Delivers very high bandwidth density. So that basic premise here is that dies can be manufactured anywhere and assembled anywhere by any OSAT, just like you do things on a board. It's a mix and match thing, and an open chiplet based ecosystem. Now, UCIe offers the best key metrics, and it is supposed to meet the projected compute demands for the next few years. Not that we are sitting still either. We will continuously innovate. We support multiple data rates for the planar. You can see 4, 8, 12, 16, 24, 32. And as I mentioned earlier, with 3.0, 48 and 64. UCIe 3D is the vertical interconnect. It runs slow, but there are a lot more wires running. So you get very high bandwidth density with very low power. Again, not today's topic, but you can look into those. This is the width of every module per direction, 16 data wires each direction for standard, 64 for advanced. A UCIe link can be 1 module, 2 modules, or 4 modules. And you can have multiple UCIe links if you want even more bandwidth. We talked about the range of bump pitches, the channel reach here. Now, this is where the metrics come in. So there are 2 metrics for bandwidth density. One is the shoreline density, gigabytes per second per millimeter, and the other one is aerial density. And these depend on the frequency. And these are basically at 110 micron for 2D and 45 micron for 2.5D. So the lower number, like 28, is what you get if you are running the link at 4 gig, 16 lanes that is. And if you run at 32, you're going to get 224 gigabytes per second per millimeter. And again, as the bump pitches shrink, these numbers are going to go up because as your bump pitch, for example, if you go from 45 micron to 25 micron bump pitch, you get 3.25 times more number of wires, right? So that improves your bandwidth density. How does it compare with external interconnect? Things like PCI Express or CXL, those are double digit in terms of gigabytes per second. So you are getting 1 to 2 orders of magnitude more bandwidth density with planar and another 2 to 3 orders of magnitude higher bandwidth density with vertical. Power efficiency numbers 0.5, 0.25. Again, external links are at around 5 to 10 picojoule per bit. You also get this dynamic power savings, so you can turn things on or off quickly. Less than a nanosecond is what it takes, and you get 85% power savings. External links are in multiple microseconds to do that. And the latency is also fairly low. It's 2 nanoseconds for the round trip from the transaction layer down and up. Like CXL, it is at least an order of magnitude more, and other links have even another order of magnitude higher than that. So very good key metrics, and that's basically the reason why we think this is a good solution for the memory, solving the memory bandwidth challenges. Now we'll talk about some of the approaches that we are proposing in this paper. You can look at the paper for more details. Now, our approach is to use the UCIe PHY as well as the UCIe's die-to-die adapter for memory access. So we have proposals here that are for the standard UCIe width, symmetric width, like the ones we talked about. We also have are proposing things where you can change the widths, but it is the same UCIe PHY and the same UCIe die-to-die adapter, just that different data widths in the different directions. This is the asymmetric one. There are two broad categories, right? Two broad architectures. So one of them is that the memory is connected through a logic die. So in this example, you got SoC, you connect using UCIe to the logic die, and the logic die then in turn connects to a stack of HBM, or in this case, in the second case, it connects to a stack of LPDDR dies, right? And this can be wire bonded in the LPDDR case. This PHY can be, by the way, LPDDR PHY, or they can even be UCIe PHY. This is a much more easier intercept, right? The industry is already moving towards logic die being in the logic process node. The next one, which is the memory die, has its own native UCIe. That's much more longer term. And this is where, we can think of the LPDDR dies, for example, having a native UCIe PHY, right? It needs a lot more changes to the ecosystem. So again, the memory controller can be either on the SoC or it can be on the logic die, and the proposals comprehend both of them. They all have their own plus and minus. The protocols that we are mapping are CXL, of course, CXL.mem, and we also have a flavor of, we are proposing a flavor of CXL.mem with some optimizations that we will talk about. Chai, and again, that is this is the internal IP protocol from ARM. We have not made any changes to that. We are mapping it as is, and therefore, for the sake of completeness, with optimizations, this can also look pretty good. And then we are mapping LPDDR6 and HBM4 protocols along with the timing as is on the UCIe PHY. So now let's look into LPDDR6 protocol mapped onto an asymmetric UCIe link. Now there are two categories like we talked about. One of them is where the memory, there is a logic die, and here the memory controller is on the SoC, and the logic die acts as a multiplexer, demultiplexer. The other one is a native connection to a LPDDR die using UCIe. So the UCIe is asymmetric because we are optimizing for read and write ratios differently. In general, you expect more reads than writes. And again, you can go with a different ratio. And then there are certain things like command only moves in one direction. So, that's the reason why it is asymmetric in nature. So in the first case, at 74 wires, that is over here, the read is, you can see the read has got 36, the write is 24, so 3:2 ratio. And this closely mimics a BISIC32 UCIe. You just add another row of bumps for the extra data wires. The other option is, the second option that we are talking about is the direct connect. And this is, again, 2:1 ratio with 43 or 45 wires. And 45 is if you make some more changes here and want to get even more bandwidth out of the LPDDR device. The details are there in the paper for you to look at. The key here is the LPDDR protocol and then the timing. Those are maintained as is. So if you look into this is the signal list for a two sub-channel by 24 LPDDR6. You got, let's say, 8 command address wires that run at half the frequency, 2 chip select wires. So those two, when we map it into the UCIe, we will map using 4. Right? We're going to take the all the encodings and map it using 4 wires, and it runs at full frequency. That's why it is, effectively anything that is half will have about half of that. So we go on mapping in that particular way. And then, of course, we have to add our UCIe clock, track, valid. Those are the extra ones for the data. CRC, for example, is there on the UCIe side. It is not there on the LPDDR side. So those, we have accounted for all of those. And we end up with a total of 51 wires versus 46. So slightly higher number of wire count, but then the thing is we get a lot better in terms of the bandwidth density that we will see. So that's the idea. Now, this is showing a timing diagram of the approach that I just talked about. And of course, I can't go through this in a lot of detail. I'll go through some highlights here, right? So there are 4 parts to it. The time goes like from 0 to 31 here, and then 32 to 63, and then 64 all the way to 127 here, okay? Now you can see that basically there are 4 LPDDR6 on the that are connected to the dies that are connected to the logic die. This is the UCIe clock, and then this is the device clock, runs about 1/4 of the UCIe clock. And anything on the UCIe command, let's say I send commands, 4 sets of activate command for the 4 LPDDR6 dies. Those will show up after 32 UI. The logic die accumulates them and then presents it onto the LPDDR6 interfaces, the four sets of LPDDR6 that it has, and it sends the activate there. Then the second set of activate comes and it will be showing up in the following 32 UI. Now let's look into some read that was going on the device side, so that those data that came out, those read data that were happening here, D0 through D7, and these are from the 4 LPDDR dies, they start pumping out over here, right? So effectively everything that happens in this 32 UI is reflected in the next 32 UI interval because it's a 4:1 ratio, right? That's what we have. So we are keeping the timing intact, and all that the logic die is doing is it's acting as a multiplexer, demultiplexer, and pipelines things. On the HBM4 side, it's a similar approach. Memory controller is on the SoC side. The logic die is the one that connects to the HBM stack. And here is the list of the signals that we have. Again, you can go through the paper and get all the details there. Now, for the CHI, as I said earlier, we just took the CHI protocol and mapped it as is, no optimization, nothing. And we optimize it. We're going to, of course, come up with a better option. But we mapped the CHI format X because that is better in terms of bandwidth density, effective bandwidth density than Y. It's 12 by 20 granules. So you can see that those are the 12 sets of them that we have mapped here. You can see those bytes. This is the link header. This is again a 256 byte UCIe flit header. The UCIe flit. This is the 2 byte header there. This is the 2 CRC bytes, and these are the protocol headers from the CHI protocol. So that's basically the way we mapped. We also did the mapping, of course, with the CXL.mem. Here, the memory controller is on the logic die, and the SoC to logic die is CXL.mem. There are 2 flavors. One is, as I said earlier, it is the native CXL.mem. So you got the header, you got the H slot, the G slots here, and then here, if you recall, there were few extra bytes, but then mostly it is FEC and CRC. So this is the layout that you have. Headers or responses, whether it is for requests or responses, can go in H slot or G slot, and data only goes in the G slot. Now, CXL is done for large systems, 1024 kind of servers. So a lot of the fields that are there in those in the headers, we can compress them, or we can do with less number of them. For example, I don't need 16 tag fields. access latency here is much lower. 8 is plenty, right? It's unlikely I'm going to have 256 outstanding read requests to a logic die. Okay. So if we reduce that, then what happens is that I can pack twice the number of headers in a given slot, and then I make some small changes here with this, where I move the header to down there. I get a HS slot, which is 10 bytes. So now I basically opened up one more G slot here, right? And that basically gives me more effective bandwidth density for the same link speed and link width. So now let's look into the results here. This is the microarchitecture, and again, details are there in the paper, but basically this is the analog PHY, this is the logic PHY. And as you can see, we have taken care to make sure that the latency is minimized, right? For example, when we do scrambling, descrambling, we just have an XOR, we pre-compute everything. So there is just one XOR stage that we go through, right? And then there is another one for the flit packing, unpacking. This one takes a nanosecond. It's 2 gigahertz is the internal clock here. Link speed is 32 gig. You're going to have very similar microarchitecture, whether it is an asymmetric one, just that the widths will be different. And if you go with other frequencies, again, similar numbers, you just have to modulate your internal frequency accordingly. But effectively one clock stage for every one of these stages, and you end up with 1 nanosecond here for the round trip, 1 nanosecond. Oh, my cursor is not moving fast enough. 1 nanosecond here for this round trip, and then the flit packing, unpacking is another nanosecond. So total round trip from the memory protocol layer, accounting for the flit packing, unpacking is 3 nanoseconds, right? And LPDDR5 we have measured in our implementation 7.5 nanoseconds equivalent, HBM3 6 nanoseconds. So, in the ballpark, right? I mean, slightly better with UCIe, but in the ballpark. Now, the other part of the comparison is around bandwidth density and power efficiency. So UCIe is bump limited, as I mentioned. So circuits fit within the bump area. We have taken great care to make sure that things are bump limited. So UCIe S, its source line is 1.143 times 1.54, right? That's at 32 gig, 110 micron. A, you got similar number. And for simplicity, we are making an assumption. This is an optimistic assumption, but that's fine. That helps, we want to portray the existing approaches in the best of the light. LP6 and HBM4, we are assuming to be bump limited. These are the bump dimensions, 5.8, 1.75, and 8 times 2.5. We are also assuming that the power numbers do not change, even though the frequencies change. You are putting more bumps for VSS and VDD. So we are discounting all of that. We're just going with the higher frequency number, but giving the same area and same power as the last generation. In the memory, only the data that is transferred, the cache line data that you transfer in the DQ is considered payload. Everything else is considered overhead. So things like address, command, ECC, CRC, credit, everything is going to be considered overhead. Now, reserved lanes for UCIe will also be considered as an overhead because we have already put the bump there. There is no way to reclaim it back. But I'm going to assume that because UCIe does aggressive power management, its power will be turned off. HBM and LPDDR, I'm assuming that things like bus turnaround and scheduling, all of those overhead are 0. Okay, so in other words, you can get 100% efficiency in those existing links. And traffic mix, we do X reads and Y writes. So every X reads, there are Y writes. So, this is 100% write traffic. This is 50-50, meaning one read, one write. So if it's effectively 100% write, because in order to write, you have to read and then write. And this will be like a checkpoint, right? Where you're not reading, you're just writing. This is 2 read, 1 write, 3 read, 1 write. And this is a typo here. I should have said 1 read, 100% read here. So those are the assumptions. And with that, we basically said, let's look into the bandwidth per source line for UCIe S versus LP, HBM for the multiple approaches with UCIe S that we talked about, and the bandwidth density in terms of gigabyte per second per millimeter square. Now, as you can see that these are flat, as you would expect, because I'm not assuming any bus turnaround time. It's perfectly there, efficient. Those links are switching back and forth. You've got bidirectional links there. And here, as you can see, your mileage varies because if you're doing, for example, 100% read, then all the data wires that are going on the other direction, they are unused, right? So your effective efficiency has dropped. So that's why these numbers tend to go up when you have a better mix of read and write. and then, then again they come down because it's 100% read. And you can see that the CXL optimized one in general does the best. Now CXL optimized over asymmetric one tends to do better when there is more, the asymmetry is helping you, right? And there are more reads than writes, right? So for example, more reads than writes, you will see the asymmetric one does better. But since here there are more writes proportionately, the other thing does much better, right? And again, this is where the point here is that protocol overheads needs to be also looked at, and we need to pack things really well, right? That's the key message here. But these are with 32 gig, by the way. Even at 32 gig, with standard UCIe, our numbers are very close to an HBM4 number. And imagine with 64 gig, these numbers will go up to X, so will be at par or better than HBM4, right? Now, this is same thing with UCIe, similar observations. And here, as you would expect, of course, your bandwidth density is going to be significantly higher with UCIe because you're comparing things that was already very high bandwidth density to begin with. And with, again, once the data rate goes twice as much, the difference will go up, right? Even more. Power efficiency wise, again, the thing to compare is HBM4 because this LP is designed for a board interface, and you can make optimization to the point where you can say that, hey, if I'm optimizing for on package, I'll eventually end up here. But this is just, again, to give you ballpark kind of number. And as you can see that, the numbers even for power efficiency, it changes with UCIe, and that's the inherent nature because it's not a bidirectional link. So, some cases you are just burning the 15% power, right? You just don't know when the other direction will get used. And UCIe, as we expect, would do better than HBM4, but they're about, in that same 0.5 to 1 picojoule per bit kind of range, right, across the entire spectrum. So, in conclusion, right, I mean, the biggest benefit that we get with UCIe is the bandwidth density. We have power advantages, we have latency advantages also. Starting point, in my opinion, would be the HBM stack because people are already talking about taking that logic die and moving it to a logic process technology so it can run faster. So use the faster PHY, get the advantage in terms of the bandwidth density, and of course, you're going to get in the process power advantage. And yes, the unidirectional nature is going to hold you back, and that's the reason why you see the graph going up and down like that. But again, those numbers are significantly better than what you would get with a bidirectional link. In the longer short term, we are going to get a frequency upgrade with the 64 gig. UCIe has the advantage that because it is bump limited, as the bump pitches go down, technology will make the bump pitches keep going down. You're going to get even more bandwidth density. So you're going to take advantage of that. And in the very long run, if you need really very high bandwidth, we can think about UCIe 3D. Memory can be on top of the logic die, and there you have anywhere from 4 to 300 terabytes per second per square millimeter square, depending on what bump pitch we are at, right? So this is a good way for us to build those kind of balanced systems. And of course, the challenges are going to be there for on-package memory for everybody, which is that, reliability, availability. How do you deal with memory failures, right? I mean, what kind of RAS mechanisms you have. So those are going to be a common set of things that with more and more memory getting integrated into an SoC, it's a common set of problems that we all need to solve. So that's all I have. And thank you. If there are any questions, we can have those. Let us see.
Yes, so we have 1 minute, so just one question on the Slack. Can you elaborate more on the round trip latency of 2 nanoseconds? For example, if sending a packet from one source UCIe to destination UCIe, is round trip protocol adapter physical layer plus the destination as well and back?
Yeah. It is the first bit to the first bit coming back. So think of it in that way. And then, so think of it as to go through, there is like a pipeline stage in each and every one of them. And it is a 2 gigahertz clock. So 3 sets of flops, right, is what you need to go through. So 3 times 0.5 in one direction and then 3 times 0.5 in the other direction. That's basically what gets you to 3 nanoseconds. Yeah, of course, you're going to have some amount of flight time, but that's negligible when you, given that these are 2
with
millimeter,
assumption
25
of 2
millimeter kind of.
gigahertz flap
Yeah,
per
yeah,
each interface. So
yeah.
that's important too. Okay.
Yeah.
I think we are right on time. There is another question, but Debendra, we can take a look on Slack.
Okay.
And with this one, we conclude technical session D. And I'd like to thank Debendra and Bardia and let you to the rest of the conference. Thank you.